Hello friends, today I will talk about frame of reference, which is a very important concept of Newtonian mechanics. This frame of reference is actually a coordinate system with some clock with respect to which we determine the position or motion and time of an object. So whenever we are talking about the motion of some object, then we have to consider one coordinate system which is having some clock also to describe the motion of the motion object under consideration. One example of a good frame of reference is the Cartesian coordinate system along with an attached clock. So whenever some object is moving, then we can determine its motion with respect to this Cartesian clock with the help of along with the help of an attached clock. Now this is why, because we need a frame of reference, because every motion is relative. So whenever we are talking about motion of certain object, then actually we have to tell that this motion is relative to some object or some frame of reference, and because of that the motion of same object appears completely different when observed by two different frames of references, or you can say when observed by two different observers. There may be disagreement between the observers about the same motion, but both the observers or all the observers will be same in their will be true in their observations, or will be correct in their observations. The only difference that is observable here is because of the observation is being carried out from different frames of references. So we can say that there is no single absolute or rest frame of reference in case of classical mechanics. So the motion depends upon the frame of reference from which it is being observed. Now here we can consider one example of a frame of reference. In this case, a person is sitting inside a train which is moving with a constant velocity v in this direction. So this person, when observed from the train frame of reference, is actually at rest with respect to the train. But when we observe the same person from the railway platform, then since the train is moving forward at a constant speed with respect to this railway platform, so this person is also moving at a constant speed in the same direction that of the train's direction with respect to the railway platform. So the same person is at rest with respect to the train, but when observed from the railway platform, it is moving with respect to the railway platform, and it is moving in a direction similar to the direction of the train's movement, and its speed is also the same as that of the train. So same person appears to be different when observed from two different frames of references. Let us consider another example, which is the example of a person standing on the earth. So when this person is observed from the ground, then this person is actually at rest relative to the ground. But when the same person is observed from the frame of reference attached to the sun, then this person will appear to be moving with the earth relative to the sun. So again, the same person is either at rest when observed from the ground, or appears to be moving along with the earth when observed from the sun. So the motion of a state, so the position, the condition of a state, condition of rest or motion is relative, and it depends upon the frame of reference from which it is being observed. Now all the frame of references can be classified into two categories. every frame will fall into one of these two categories. Either it is an inertial frame or it is a non-inertial frame. So inertial frames are also known by the name of Newtonian frame of reference or Galilean frame of reference, whereas non-inertial frames are actually the accelerated frames of reference or fictitious force frames. Now these new inertial frames of reference are those in which Newton's first law, that is the law of inertia, holds good. And since Newton's first law is a special case of Newton's second law, so Newton's second law of motion also holds good in case of inertial or Newtonian frames of reference. These are actually non-accelerating frames of reference, and these are also non-rotating frame of reference. So because of this, if a body has zero net real force acting over it, then this body will stay at rest or it will move at constant velocity, because there is no acceleration of the frame itself. So the frame is not changing the motion of the body. Any frame which is moving at constant velocity relative to an inertial frame is also an inertial frame. So if there is an inertial frame and another frame is moving at constant velocity with respect to the inertial frame, then the second frame will also be an inertial frame. And in case of inertial frames, no fictitious force is needed. All inertial frames have a common time or the same time. Some examples of inertial frames can be considered over here as a laboratory approximately at rest on Earth, a train or car moving in a straight line at constant velocity, a frame attached to the distant or fixed stars. All these are examples of nearly inertial frames of reference. There is no absolutely inertial frame of reference existing in the universe. Now, as I talked about, non-inertial frames are actually the accelerated frames of reference. So in this case, the frame itself has some acceleration or it is rotating relative to an inertial frame. In both the cases, either linear acceleration or the rotational acceleration, the frame will be a non-inertial frame. And in this case, Newton's law in their original form cannot be directly applied. We have to modify Newton's laws by considering or by involving a fictitious or pseudo force or apparent force to apply these Newton's laws to the problems discussed in non-inertial frames of references. Now, one important fact about these non-inertial frames is that the motion of an unaccelerated object appears to be accelerated when observed from a non-inertial frame of reference, and it is a consequence of the acceleration of the non-inertial frame itself. So since the frame is itself accelerated, it will change the motion appearance of the motion of the object. Now, since fictitious forces are involved in non-inertial frames, so fictitious forces actually are not real forces, so these cannot be measured by real instruments. Some examples of non-inertial frames are an accelerating car or a train which is applying brakes, a turning merry-go-round, or a rotating turntable. The rotating earth, strictly speaking, is non-inertial frame. So earth actually for practical purposes is taken as an inertial frame, but if we strictly talk about earth, then since it is continuously rotating about its own axis as well as it is revolving about the sun, so it has got some acceleration, although that acceleration is very small. So earth is exactly a strictly speaking a non-inertial frame of reference, but because its acceleration is small, so we consider it for practical purposes to behave as an inertial frame. Now here I have shown the inertial versus non-inertial frames in action. The key difference is the acceleration of the observer's own frame. Here a person is sitting inside this car which is moving with constant velocity in this direction, and this person is dropping a ball from his hand. So the person is dropping a ball from his hand, then this ball will move with the same horizontal velocity v in the same direction. Okay, so observer O is moving at constant velocity. This the velocity is that velocity with which the car is moving. A ball is released from the hand, and that ball maintains the same horizontal velocity, and this will happen only when the air resistance is completely neglected. So in this discussion, no extra force is involved. Some more examples can be considered over here is an elevator or a lift moving at constant speed. Another example may be taken over here is airplane cruising steadily, straight line and on a level. Not it is increasing its height or not, neither it is decreasing its height. Another example of one example for non-inertial frame is actually an accelerating frame of reference. So here we consider a car which is moving with acceleration a in this direction, and the same person is sitting over here, and he or she is dropping a ball from his hand. Then in this case, now the ball will move backwards, and its acceleration will be in magnitude equal to this magnitude of the car, but the direction is opposite. So this is because of the acceleration of the car itself, or that is the frame itself. So an elevator speeding up or slowing down is an example of a non-inertial frame of reference. Another example is a spacecraft firing its thrusters. Now the fictitious or pseudo or false force acting appears to be acting on the object is given by this formula: F fictitious equal to minus mass times acceleration of the frame of reference minus m into a frame, and this force always acts opposite to the acceleration of the non-inertial frame itself. Here I have considered one numerical example to calculate different types of forces in this problem. So the problem is of an accelerating train. So this train is accelerating with an acceleration a equal to 2 meter per second square in this direction, that is the east direction, and a person of mass 60 kg is standing in this train. So we have to calculate the true force acting on the person, the fictitious force, that is the false force, and the net observed force on the passenger. So we can calculate from here. So true force, and this basically we are calculating with respect to the ground frame. So that is the inertial frame. So this real friction force from the floor accelerates the passenger with the train, and this true force will be equal to mass times the acceleration, that is 60 into 2 equal to 120 Newton directed east. True force will be in the same direction as the direction in which the train is accelerating. Now since the person is sitting inside an accelerating train, so train's own frame will be non-inertial frame, because train is accelerating with respect to the ground. So this train's own accelerating frame is actually a non-inertial frame, because it is an accelerating frame of reference. So the fictitious force acting on the person will be given by this F fictitious equal to minus m times acceleration of the frame itself, that is minus 60 into 2, that is 120 Newton. Now the direction of this fictitious force will be opposite to the direction of the actual movement of the train. So it is directed west, since the train is moving in the east direction. Now the observed or net force in the train will be the combination of, or the resultant of, true force and the fictitious force. So true force is acting in the east direction and magnitude is 120 Newton, whereas the fictitious force is acting in the west direction and magnitude is again 120 Newton. So this will be with a minus sign, so the resultant will be 0 Newton. So the observed force on the person is standing inside the train will be zero, and because of this zero net force, the person stays at rest with respect to the train. It is not in motion, or it is not accelerating or deaccelerating with respect to the train. In another example, I have considered force on a rotating platform. So here is a rotating platform. A ball of mass 0.20 kg is tied by a string and rotates with a platform of radius r equal to 0.50 meter at angular velocity this much. So we have to again calculate the three type of forces. True force, that is the tension force in the thread string, the fictitious force, which is the centrifugal force here, and the net observed force, which is the combination of the two forces. So in this case, this is the center of the platform, and the tension force, that is the centripetal force, is acting radially inwards, whereas the centrifugal force or the fictitious force will act in a opposite direction, that is radially outwards. So it is shown by this arrow. So we can calculate true force, that is the force with respect to the inertial frame, that is the ground frame. So this will be the centripetal force, F2 equal to mass times acceleration, and acceleration is r omega square, so m omega square r. So this comes out to be 1.6 Newton towards the center of the platform, circular platform. Okay. Then fictitious force, which is appears to be acting in the rotating frame or the non-inertial frame. It is actually the centrifugal force. So this will be equal in magnitude but in opposite in direction to this true force. So again it is 1.6 Newton, but it is now directed away from the center. And in the third, we have calculated the observed or net force on the wall, so which will be the resultant of these two forces. So 1.6 Newton acting inwards and 1.6 Newton acting outwards. So the net result is 0 Newton. So because of this net force being 0, the ball keeps rotating with the platform. It is not leaving the platform, or it is not flying off the platform. So this was actually the discussion of frames of references and associated concepts. Hope you will enjoy it, and in the next lecture I will discuss about the two important fictitious forces, that is the Coriolis force and the centrifugal force, and their effects. Till then, thank you. Bye bye.